The turbines are already spinning, not in a laboratory, not in a test facility, in the open ocean, kilometers from shore, pulling energy from currents that never stop moving. Nobody announced it with a ceremony. There was no ribbon. The machines simply started running. What they are part of is a project so large that the engineers who designed it had to invent new units of measurement to describe it. And if it works, if it actually works, it could be the last energy project humanity ever needs to build. For most of recorded history, the problem of energy has been the same problem. Where is the fuel, and how do we burn it? Coal, oil, natural gas. Each one a buried store of energy that took millions of years to form and took us roughly 2 centuries to burn through half of. The replacement technologies, solar, wind, nuclear, each solve part of the problem. None of them individually solve all of it. The proposal at the center of this video solves all of it. At least, that is the claim. The project, estimated to carry a price tag of around $2 trillion across its full build-out, is not a single structure. It is a system, a layered, interconnected network of generation, storage, and distribution technology designed to function as the world's first planetary-scale energy grid. The formal concept emerged from a series of engineering studies commissioned through international energy bodies in the mid-2010s. The driving question was simple. What would it actually cost to end dependence on fossil fuels, not just reduce it, but end it? The answer came back in phases. Phase 1, build out. Phase 2, connect. Phase 3, stabilize. Total cost, at the time, was estimated at somewhere between $1.5 and $2.5 trillion, spread over 30 years. That number was both enormous and, in a different framing, surprisingly manageable. The global energy industry already spends roughly $400 billion a year on maintenance and new fossil fuel infrastructure. Over 30 years, that is $12 trillion. The proposed system would cost, in comparative terms, 1/6 of the baseline alternative. The economics were not the obstacle. The politics were. To understand who is driving this now, you have to go back to a specific meeting in Copenhagen in 2019. A coalition of sovereign wealth funds, primarily from Norway, the Gulf states, and parts of Southeast Asia, quietly commissioned an independent feasibility review. The document they received back was classified for nearly 2 years. When portions of it leaked, in 2021, the language inside it was striking. It did not say the project was ambitious. It said the project was buildable. That was the word, buildable. The engineering core of the system rests on 4 technologies used in combination, rather than in isolation. First, offshore wind arrays, specifically designed for deep water using floating platform foundations, rather than the fixed-bottom turbines common in shallow European waters. Floating platforms allow placement in the deep ocean, where winds are stronger and more consistent. They can be anchored in water 300 meters deep or more. Second, utility-scale long-duration battery storage, primarily using iron-air chemistry, which stores energy for days or weeks rather than hours. Iron-air batteries are far cheaper to manufacture than lithium-ion at large scale. Several facilities using early versions of this chemistry are already operating in the United States and Germany. Third, high-voltage direct current transmission lines, capable of moving electricity thousands of kilometers with minimal loss. These cables already exist in prototype forms connecting parts of Europe and North Africa. Fourth, and most controversial, space-based solar collection. This is the component that has attracted the most skepticism and the most funding. The concept involves placing large solar arrays in geostationary orbit, where they receive sunlight 24 hours a day with no atmospheric interference, then transmitting that energy to ground-based receivers using microwave or laser beams. The technology is not science fiction, it is engineering, expensive engineering, enormously complex. but testable. Japan's National Space Agency has been running transmission experiments since 2015. The European Space Agency published a formal roadmap for space-based solar in 2022, outlining a path to a demonstrator satellite by the mid-2030s. The projected cost for that single demonstrator, around $800 million. Scale that up to a functioning grid contribution, and the number grows considerably, but the underlying physics have been demonstrated. Light can be converted to energy in orbit. That energy can be beamed down, not a theory, not a sketch, a tested, repeatable result. So why is it not already happening? This is the question that takes us into the real difficulty of the project. Not the engineering, but the coordination. To build a system like this, you would need simultaneous agreement from dozens of governments on undersea cable rights, satellite orbital allocations, grid interconnection standards, and shared liability frameworks for energy that crosses national borders. That is not an engineering problem. It is a governance problem. And governance problems, historically, take longer to solve. Here is what changed. In 2022, the energy disruptions caused by the war in Ukraine forced a reckoning in European policy circles that had been building for a decade. The price of natural gas on European markets spiked by roughly 300%. Several governments that had been comfortably deferring long-term energy transition planning suddenly had no comfortable position left to stand in. Emergency summits produced emergency commitments. Emergency commitments produced over the following 18 months something rarer, actual legislation. The European Union's REPowerEU plan, launched in 2022, committed hundreds of billions of euros to accelerated energy independence. Parallel commitments emerged from South Korea, Japan, and Australia. The Gulf sovereign wealth funds that had quietly commissioned the 2019 feasibility study began making public statements about diversification. The money was not all the same money. The goals were not all the same goals. But they began moving in the same direction at the same time. That convergence is what gave the $2 trillion framework its present momentum. No single country is building this. No single company, no single treaty obligates anyone. What is happening instead is something more organic, and in some ways more durable. Dozens of separate entities, each pursuing their own version of energy security, gradually building components that fit together. The North Sea floating wind farms being planned by Denmark and the United Kingdom, the iron air battery deployment scaling up in Michigan, the high-voltage cables being laid from North Africa toward Portugal, the orbital solar demonstrators being developed by Japan and Europe. Separately, each of these is a significant infrastructure project. Together, they are the beginning of the system, whether the people building them intend it or not. The obstacle in this story is not a single dramatic failure. It is a slower problem, and in many ways a harder one. The grid itself is designed for the world as it was built, not the world as it needs to function. In most countries, the electrical transmission infrastructure dates from the mid-20th century. It was engineered for a few large power stations feeding outward in one direction, not for a networked system where generation can come from floating platforms off the Scottish coast, or from a satellite receiver station in the Sahara, or from a battery farm in Ohio. Rebuilding that grid, not just extending it but fundamentally redesigning it, is, by some estimates, as large a project as the generation build-out itself. The International Energy Agency has estimated that grid investment globally would need to triple by 2030 just to keep pace with the energy transition already underway. Tripling from a current baseline of hundreds of billions annually. In 2023, a coalition of grid operators from 11 countries published a joint assessment. The language in the executive summary was careful, but the conclusion was plain. Without coordinated grid investment, renewable generation capacity would keep being built, and keep being unable to deliver power where it was needed. You could fill the ocean with turbines. If the cable could not carry the electricity to a city, the city would still go dark. That was the moment some of the project's architects, working across different institutions on different continents, recognized the problem had shifted. Generation was being solved. Slowly, expensively, but solved. The grid was not. The breakthrough in framing, when it came, was not technical. It was conceptual. Instead of treating the grid as national infrastructure, owned by individual countries, governed by national regulators, optimized for national needs, a small group of policy engineers began arguing for treating it as shared infrastructure, like the international banking settlement system, like the internet backbone, a thing that belongs to no single owner, and functions precisely because of that. The legal architecture for this does not yet exist in full. The treaties required to govern it have not been written, but the precedents are there in maritime law, in aviation rights, in the standards bodies that govern how computers talk to one another. Building on those precedents, drafting the governance frameworks, is now the active work of several international legal teams. It is slow work. It produces no ribbon-cutting moment, no photograph of a completed structure, but it is arguably the most consequential work of the entire project. What would the world actually look like if this works? Energy economists have modeled several scenarios. The most discussed projects that by 2060, if the system reached even 60% of its theoretical capacity, the global cost of electricity could fall to a level that would make fuel poverty, the condition of not being able to afford heat or light, largely eliminable. Not everywhere at once, not equally distributed, but for the first time in history, a world where energy is genuinely cheap enough to be accessible to essentially everyone is a world described by physics, not just by politics. That is not a certainty. Many things can intervene. The governance frameworks may not get written fast enough. The grid investment may not materialize. Geopolitical conflict could fragment the international cooperation the system requires. Some of the underlying technologies may underperform at scale. $2 trillion does not guarantee an outcome. It buys a serious attempt at one. What it represents more than anything is a calculation that enough powerful actors have made simultaneously, that the cost of trying is lower than the cost of not trying. That calculation, once made, is hard to unmake. The turbines in the deep water keep turning. The battery farms keep filling and emptying. The satellites keep circling. The grid is being rebuilt, quietly, cable by cable, law by law, agreement by argument. Whether it finishes or fails, it will leave a mark on how the next generation builds. The story of this project is still being written, and the people writing it are working in a dozen languages, on 4 continents, on a timeline that outlasts any of them. That may be the most human thing about it.